One of the strengths of NMR spectroscopy is the wide variety of nuclei it is capable of detecting. A quick look at the periodic table reveals that almost every element has at least one NMR active isotope. The vast majority of NMR applications concentrate on elements frequently occurring in organic or biomolecules, such as proton, carbon, and phosphorus. In inorganic chemistry, problems are often associated with other members of the periodic table. Protocols to set up NMR experiments for the common nuclei are readily available in VNMRJ and can conveniently be accessed via the experiment selector. It would, however, be impractical to supply protocols for every NMR active nucleus in the standard software and populate the user interface with buttons the operator will never need. Instead, VNMRJ3 supplies a set of very easy and robust tools to allow customers to add protocols to detect their favorite nuclei or set up different pulse sequences with those nuclei involved. In the current example, we consider a group of chemists dealing with molecules containing boron. They would like to record 1D boron survey spectra as well as a 2D boron COSY map to monitor boron-boron connectivities. We start with converting an existing carbon protocol to boron-11, do the necessary RF calibrations, and from there, we create a 2D protocol allowing the chemists to set up boron-boron COSY experiments by clicking a single button in the experiment selector. We are using a 500 MHz DD2 spectrometer equipped with a 1 NMR probe. A vinyl decaborane sample has been placed into the magnet, it is locked and shimmed, and the probe is tuned to the respective B11 and proton frequencies. First, we go to the experiment menu and request B11 detection. We do not yet have a B11 parameter set, therefore, the default C13 parameters are recalled and the transmitter nucleus gets converted to B11, defining the proper spectrometer frequency. We start from here and build a parameter set for B11, either based on experience or on literature data. We set the pulse sequence label to boron-11 in the command line. This is more representative for the acquired data than the name of the pulse sequence, which is nucleus independent. The spectral range of plus or minus 100 parts per million may be just fine. Boron-11 is significantly more sensitive than C13, so we can decrease the number of scans to 16. Due to its quadrupolar nature, boron relaxes much faster than carbon. Therefore, we can reduce the acquisition time to 50 milliseconds and the relaxation delay to 10 milliseconds. Finally, we select a 10 Hz line broadening and set the Fourier size to 16K. When all the desired changes are complete, we save this file as the default protocol for B11. We can do that via the Tools menu. The new protocol button will be labeled as boron-11, and we put it into a new experiment tab called boron. We may do further customization here if we wish. As an example, we choose a 90-degree observation pulse. We save the parameter set and close the panel. In the experiment selector, a new boron tab appears with the requested boron-11 button in it. At this point, we can test our new protocol to verify that it functions properly and delivers the boron spectrum we expect. When clicking the Acquire button, data acquisition begins, and data processing takes place automatically once the acquisition is complete. By zooming into the signal region, 6 well-separated lines are displayed. Although vinyl decaborane has 10 boron atoms, due to symmetry reasons, there are 4 magnetically equivalent boron pairs. These are seen on the right with doubled intensities. While customizing the parameters, we requested a 90-degree excitation pulse, but our probe file does not contain calibration data for B11 yet. The pulse width that we just used was a leftover from the C13 parameter set. Now that we have a working B11 protocol, we can quickly perform a pulse calibration. The high boron sensitivity allows us to run the calibration with a single scan. We make use of the parameter array capability of VNMRJ. We request the PW parameter to be arrayed, ask for 25 values, starting from 2 microseconds and gradually incrementing it by the same amount. The result is a pulse width array from 2 to 50 microseconds. We close the window and acquire the data. The second null appears at 40.4 microseconds that corresponds to a 10.1 microsecond 90-degree pulse width. at a lower level of 57 dB. This information is probe-related, so it should be stored in the probe file. There are tabs for several nuclei in the probe file, but B11 is obviously missing. We add a new B11 tab to the file using the Add Nucleus button. We enter the 90-degree pulse width and the power level. Save the changes and close the probe panel. This way, the next time we use the boron protocol, we'll get the requested flip angle. We continue by creating a gradient COSY protocol for B11. Our starting point this time is the G-COSY protocol that VNMRJ has by default for protons. We clone this protocol and make it boron compatible. By double-clicking on the G-COSY protocol, the COSY-related parameters are loaded to the current workspace, ready to be customized. A proton COSY is typically set up from a proton spectrum. Similarly, a boron COSY should make use of a boron 11 spectrum if it is available at the time the 2D experiment is requested. We continue by setting the acquisition time and the relaxation delay, and reducing the number of steady-state pulses to 4. Next, we deselect the steady-state block at the beginning of the sequence and force the evolution time to start from 0. Finally, we turn on broadband proton decoupling during both the evolution and the acquisition period, and set the modulation scheme to waltz. When ready, we save the new protocol under the name B11G-COSY in the Boron Experiment tab. We have just created a new button in the Experiment selector. Our new boron and boron COSY protocols are ready to be tested. Clicking on boron 11 and the Acquire button, we have the boron survey spectrum. We may zoom into the signal region, narrow the spectral window, and click on B11G-COSY to set up the 2D experiment. After a few seconds of acquisition, the COSY map reveals an extensive coupling network among the boron atoms. Interestingly enough, these interactions remain hidden in the 1D line widths due to fast boron relaxation. As we have just seen, adding a boron and boron COSY button to the experiment selector is a fast, easy, and robust process. The new protocols are fully integrated with all the other features customers have come to expect from VNMRJ 3.